My name is Mike DeLaCluse, President of Lesman Instrument Company. I'd like to thank everybody for taking time out of their busy schedules to join us for today's webinar, which is Flame Safety 201. It's the second in our series of 3 sessions on flame safety, with one more to follow on March 21st. Today's presenter is Dave Shunn. Dave is Regional Sales Manager for Fireeye with responsibilities for distribution and OEM customers in the Midwest. Dave has 30 years of experience dedicated to flame safety, having worked for manufacturers and distributors of both controls and burners. When with customers, he helps troubleshooting, startup assistance, and incident investigation. You'll find Dave's style light and lively with an emphasis on the practical. Because of the large number of attendees, we have the phone lines muted. If you have a question, please type it into the chat tool so we can respond. There's a question box there with the toolbar. Go ahead and put in your question, and I'll have Dave answer it as they pop up. Dave, with that, go ahead and take it away.
Okay, thanks. Good morning, everybody. We'll start out with a review of what I call the sequence. The sequence is the basic operational pattern for all flame safeguards, whether they are made by us or others. The sequence starts out in standby. The operating control is satisfied. Next, the operating control will close. That will tell the flame safeguard that there is a call for heat. On a E110 made by Fireye, that would be terminal 13. Also, all the limits have to be made at that point. So if in a situation where there should be a call for heat, but you're not experiencing that, you would want to check power at the main breaker, and then you want to check the limit string one by one and see what device will be holding you out. Current modern controls also have first out enunciators as an option, and that would pinpoint what device would be holding you out. The control then moves into a safe start check, where the microprocessor will verify the state of the terminals for both inputs and outputs, do a sum check on the microprocessor itself, verify everything's ready to go. We then start pre-purge. Pre-purge is simply blowing air through the combustion chamber. Codes require a minimum of 4 air changes. So to do pre-purge, we start a blower motor, and then an airflow switch must prove that there is airflow and report that back to the flame safeguard. The next event that occurs is pilot trial for ignition. At that point, we're opening up the pilot valve. The gas pressure must be correct. We are also energizing an ignition transformer, which must produce spark in the combustion chamber. And finally, a flame detector must sense that there is a flame and report that back to the control. After that, we move to main trial for ignition. The main valve must open. Again, the gas pressure must be correct. There must be proper airflow. And the pilot must be of adequate size and position to light the main flame. We then go into the run period, and that will continue until the controller is satisfied. When it's satisfied, the controller opens, and that ends the call for heat. And an internal latching relay will generally do a post-purge, so that the blower will clear the combustion chamber of any byproducts. Just open up my box there. I don't believe we have any questions at this point. No.
No questions at this point, Dave.
Okay. I was having a problem when I opened up the dialog box. The PowerPoint wasn't advancing, so I closed that box. Here's a typical primary control for Fireye Micro M. Similar control would be a Honeywell RM7890 or RM7895. The Fireye flavor of it.
Dave, it doesn't look like your slide is advanced.
No. There we go.
There you go. Now you got it.
The controller is going to have a chassis for a Fireye version. There will be a wiring base, a programmer, which plugs in on the right side of that chassis. An amplifier plugs into the center section. and then there's an optional display. If we look at that wiring base, you can see there's 10 terminals with various inputs and outputs. And again, this is specific to a Fireye control, but we're just going to follow the sequence of operation and look at the wiring diagram and see how things are moving along. On this slide, there's my pointer, you can see that L1 is hot, and that remains hot either in standby or during the operation of the control. That way we can record any off-cycle lockouts. So the first thing that happens is that the operating control closes, and we have power on our terminal 7. Upstream of that electrically, there would be the limits, such as maybe high and low gas pressure switches, low water cutoff, that sort of thing. Once that control senses the need for heat, it turns on the blower motor, and in our programmer control, the operating control LED is lit. This slide is incorrect in that there should be power along this coming off of 1. It should have been hot up to the KB relay, and then when that relay makes, that is what energizes terminal 8 and the blower motor. After that, we wait 10 seconds for the motor to get up to speed, and at that point we need to prove the airflow switch closed. If we don't prove that airflow switch closed within 10 seconds, we will go to lockout. This slide, we're trying to just highlight the things that change, but you have to remember the operating control would still be hot at this point, and the blower motor would still be running, even though the colored lines have now shifted to the new device that we added in the sequence. Once the airflow switch makes, the control initiates pre-purge. Up in the right-hand corner, you can see the airflow LED is now lit. Pre-purge is selectable on our control by dip switches. Once that purge times out, then we go ahead and energize the ignition transformer off of terminal 4 and the gas pilot valve off of terminal 3. And again, I just want to remind you, operating control is made, airflow switch is made, blower motor is made and running, and then terminal 1 is also made. Once we start our pilot trial for ignition, which is unsupervised, and that we will keep the pilot valve and the ignition transformer on whether we see flame or not for the selected period. In the case of a Fireye, it's either a 5 or 10-second trial for pilot. But it's a good day, and the pilot lights up here. At that point, the flame relay pulls in, and our normally closed contact opens. Our normally open contact closes, and by means of that, we drop the ignition transformer and open the main fuel valve. Pilot trial for ignition is complete. Main trial for ignition is done. Here, with the exception of this circuit, I don't know why that one wasn't colored. We are now in the run mode. We will continue in that mode until the operating control is satisfied. You can see that the flame LED is on, the airflow LED is on, and the operating call for heat LED is on. The operating control opens. Our LEDs go out. We drop power to our gas valve, our pilot, and our main. If there was a latching relay in there for post-purge, that would hold that KB in, and the blower would continue. Typically, we have a 15-second post-purge. So that's the basic wiring sequence for a primary style control, typically on-off. Any questions on that? All good.
Hold it, Dave. We've got a question. Can a value from an analog airflow meter be used in place of an airflow switch?
On a primary style flame safeguard, the answer would be no. It's not equipped for analog inputs. It needs a digital. More advanced parallel positioning controls can use airflow sensors. Some of them will have draft control built into them. But on this basic style control, it has to be digital. Anything else?
No, that's it for now. Thanks.
Okay. Yeah, the questions are only coming directly to you because I don't see them in my dialog box, so just let me know. Okay, now we're going to move on to what we call a programming control. That would be a Fireye E110, a BurnerLogix control, a Honeywell RM7800, 7840 series, those type of controls. And these are going to have a modulating circuit in them. Typically, you're going to have a low, high, low proven pre-purge and some additional interlocks. As we look at this, we see the wiring terminals there in the center. We see internally what we're driving above that line, and then the external controls on the bottom side of that. Advance. Okay, in standby, we have 120 volt power to terminal L1. We have that power coming down through the operating controls, waiting for that operating control to close. Operating control closes, and again, we're following that same generic sequence. So at that point, we power up terminal 13. We immediately look at our fuel valve end switch, which I think is the next slide there. L13 to 3, that has to be made. If the fuel valve end switch is not made, the control will immediately lock out because that would indicate that our safety valve is not fully closed for some reason, or more likely, probably that end switch is out of adjustment. But again, it's a good day today, and that fuel valve end switch is closed. So at that point, we energize the blower motor, terminal M on this series control. We also, at that point, internally start driving the mod motor for the air damper to high fire position. Again, remember the safety valve is still closed, but the mod motor is probably connected to a butterfly valve and the damper. So we're going to drive that to high fire. We also, within 10 seconds, need to prove our 3 to P running interlocks, which is our airflow switch. You remember from session 1, a running interlock is an interlock that closes on the call for heat and has to stay closed during the entire call. The fuel valve end switch would be a pre-ignition interlock, and that it needs to stay closed up till ignition. But once we get into the ignition sequence, we're going to be opening that main valve, so we no longer check those circuits. Once the mod motor reaches the high fire position, that end switch closes, and it proves terminals D to 8, which tells the flame safeguard that we are in high fire purge. And again, this is where it's important to make sure the linkage is connected and correct, and make sure that those end switches are adjusted properly, because the flame safeguard in reality has no way of knowing what position that air damper is. It only knows when that switch makes or breaks. So if a guy misadjusts that switch, you may start pre-purge too early. Okay, once that switch is made, D to 8, we Typically, it's 30 seconds for a control in this class. Once pre-purge is completed, we start to drive the mod motor back to low fire. Once the low fire switch is made, terminals M to D, we are ready for ignition. And again, the same rules apply. If that switch is not adjusted properly, it's possible to have your butterfly valve on the gas valve and your air butterfly to be open too far, and that makes for a loud light off. So proper adjustment of those end switches are critical. At that point, we energize terminals 5 and 6. Little pointer, there it is, which will be the pilot valve and the ignition transformer. Again, we call this unsupervised, in that it is either going to go for 5 or 10 seconds for gas or 15 seconds for oil. And we're going to have the ignition transformer and the pilot energized for that entire time, whether we see flame or not. So it's considered unsupervised. But it's a good day again, gentlemen. So we did prove flame. And at that point, we're going to energize the main fuel valve, and we're going to have our main trowel for ignition. This is considered a supervised event in that we may be giving it 10 seconds to light, but if any time during that 10 seconds we lose flame signal, we'll go into a lockout. So after 10 seconds, we de-energize terminal 5, which is the normal wiring for gas. This should really be a little dash line because terminal 6 is only used on oil. And then after 5 more seconds, terminal 6 is de-energized.
Hey, Dave.
Yes. Yes.
Question came up. Is there a remote reset for the alarm?
Their remote resets are available for our controls. Code says that the remote reset should be within sight and sound of the burner, but there's not a limit to that because it's typically a digital input. Okay?
Thank you.
Mm-hmm. The modulating circuit then releases to auto, in that the controller is now driving that mod motor, which is controlling the gas butterfly valve and the air damper to control the firing rate to meet the need. When the call for heat ends and the operating control opens, we run the blower motor for another 15 seconds for post-purge. We now are back in standby. L1 to 13 is open. So you can see the sequence is always going to be the same. We're just adding more permissives into it, and we're adding a modulation circuit. But again, if you're troubleshooting, whether it's a primary control or a programming control, if you follow that same basic sequence, we're always going to have an operating control that's going to close and have a call for heat. If it doesn't, we have some limit that's in that string that's holding us open. Then we go to purge, where we're going to start the blower motor. We're going to have to prove airflow and report that back to control. If it's a modulating control, we just throw in the little wrinkle of the low, high, low proven purge and the end switches in the mod motor reporting back to the flame safeguard. Once we complete purge, then again we're doing pilot trowel for ignition. Pilot trowel, we're always going to open a pilot valve. We're always going to throw spark in there, and we're always going to have some means, whether it's a flame rod or optical detector, of proving that we have fire back to the flame safeguard. If we're successful doing that, then we're always going to open up the main valves, and those will be a supervised trowel. Once we do that, we release to the controller to satisfy the need for heat. And then when that opens up, tells the flame safeguard we're done, we do a post-purge and we're complete. So it's always that same basic sequence, no matter what kind of device the control is on, and no matter who's making the control. Codes require that we follow that pattern, and it's just a matter of different terminal numbers. Any questions?
At this point, we have them all answered. So if there are questions, feel free to send them in. We'll get them answered for you. Oh, here's another one. Is there a 24-volt DC flavor of this?
There is not at this time. I'm going to skip the BurnerLogix part. I think I've covered, in essence, what we need to do there. All right, I guess we're done, huh?
If there are any other questions, feel free to send them in while I'm putting together a wrap-up. Dave, thank you very much for the presentation. If anybody does have specific application questions, feel free to give us a call at 800-9-LESMAN. That's 800-953-7626. If you're not sure who your account manager is or who to ask for, feel free to ask for me, Mike DeLaCluse, and I'll make sure that you get taken care of. The next session is going to be Flame Safety 301. And Dave, as I understand it, that's going to be all about flame detection, right?
Yes, that's going to be a session typically for multi-burner, heavy industrial use. It'll be our smart scanners that are integrated. So the flame relays built into them. They're typically dual detectors, UV and IR, and they run 21 different flicker frequencies, and we'll start to talk about the in-depth characteristics of flame, citing it, how those scanners distinguish one flame from another. Typical applications would be duct burners, petrochemical, utilities. So it's slanted that way as opposed to the more commercial type controls used in universities, manufacturing, standby boilers, stuff like that. So it's kind of a shift into a different area.
Okay. That's going to be held on March 21st, which I believe is also a Thursday morning at 9 a.m. At this point, we've got all the questions answered, so our presentation will conclude. Thank you very much for attending, and as I say, if you do have any other questions, feel free to call me, Mike DeLaCluse, and I'll make sure we get them answered for you. Thank you for attending. At this point, the session will end.
Thanks, everyone. Bye.